Welcome to the lecture series, Machine Learning. This session, we are going to concentrate on version spaces and candidate elimination algorithm of concept learning. I'm Dr. P. Uma Mageshwari, Professor, Computer Science and Engineering, College of Engineering, Indi, Anna University, Chennai. Candidate elimination algorithm. Candidate elimination algorithm normally finds all hypotheses that are consistent with the training examples using more general than partial ordering strategy. In the earlier algorithm, finders algorithm, there was a flaw, what we listed at the end of the illustration. That is, some negative examples will not be never considered by the finders. So nothing learned out of them. So, but candidate elimination, consider that also. In another difference is, finders will finally generate only one consistent hypothesis, but there could be many that is always ignored by finders algorithm. But candidate elimination look at all possible consistent hypotheses, including negative examples. It usually evaluate through. By definition, the description given here for candidate elimination algorithm can be written as a standard way, which says that a hypothesis H is said to be consistent with a given training set of examples D if and only if when it is applied to each and every example of the training set, it must return to the target concept C of X, right? So that is in turn written consistent of H comma D will be equivalent to for all example and its target concept present in the training sample D, where H of X must be C of X. This is what the definition for candidate elimination algorithm. The key difference between the definition of consistent and satisfies condition. If an example X is said to be satisfied, the hypothesis H, whenever it is 1, whenever it results 1. But whereas the hypothesis H is said to be consistent, depends on the target concept if it satisfies the target concept C of X. Now look at the version space definition. The version space is defined to be a subset of all consistent hypotheses with respect to the hypothesis space H and the training example D. By definition, in a standard way, the version space, which is denoted as capital V, capital S, H comma suffixed H comma D. This H represents the hypothesis space, D represents the training examples. With respect to hypothesis space H and training example D is the subset of hypothesis from H consistent with the training example D. So the version space is the set of all hypothesis whichever is consistent with the training example. So it can be written as VSHD is equivalent to small h is element of capital H, which is consistent in the form the H comma D. So there is an algorithm, very simple algorithm called list then eliminate algorithm, which actually helps us to find out the version space. Then eliminate algorithm is the one simplest algorithm used to understand how the version space is constructed. Here, all the inconsistent hypotheses in the hypothesis space is going to be eliminated and only the consistent hypothesis is kept. That is what the major logic behind the list then eliminate algorithm. So that is what is explained in this algorithm. In the version space, there is a list of hypotheses. For each training example, you have to check every hypothesis and whether they are consistent with or not. If they are consistent, they may result in a target concept, isn't so? So by that way, the consistent hypothesis will be h of x equal to c of x. Suppose if it is not equal to c of x, then that hypothesis is an inconsistent one, so that we have to eliminate that hypothesis. That is what list then eliminate algorithm. Right. Now, candidate elimination algorithm is simply works as per the principle that was explained in the earlier list then elimination algorithm. And this is the algorithm that represents the version space by storing only its most general members that are labeled as G and its most specific members labeled as S. And given only these two sets, S and G, the candidate elimination algorithm make it possible to enumerate all the members of the version space as needed by generating the hypothesis which lies between these two sets. That means in the general to specific partial ordering over hypothesis. General to specific partial ordering over hypothesis. So let's see how this is the algorithm, candidate elimination algorithm. So just to have a look at, once you understand the example, the algorithm is so simple to you to write by yourself. Okay. So let's begin the candidate elimination algorithm by simply initializing the two boundaries that is called G boundary, S boundary. No, so that is to be initialized. G boundary and S boundary. And G boundary initial because this is a most general boundary. So the initially G naught will be all question mark for all the attributes. This is actually for our enjoy sport example. Actually, there are 6 different attributes in there. For all attributes, any value it's ready to accept. So initially G is all question mark. But S boundary, I said it is more very specific boundary. G stands for general, S stands for specific. You please remember in such a way. S boundary set is consisting of most specific cases, no hypothesis. So S boundary is started with most specific values so that all attributes will be null, right? So every other hypothesis in H is both more general. Every other hypothesis in H is both more general than S0 and more specific than G0. With that assumption, we are moving, right? We set a boundary where G is most general, S is most specific. So whatever the rest, whatever hypothesis we find will be between these two. So that the hypothesis H will be more general than S naught, more specific than G naught, right? This is our example. Enjoy sport example. This is the given set of training examples. There are 4 examples in this set. Start initializing the S boundary. S0 is all null values and G0 is all question mark. Okay. Now start considering the examples one by one. The first example, 1 is taken, which consists attribute values sunny, warm, normal, strong, warm, same. Yeah, it's given, taken. So this the final concept here is target concept is yes. So this is a positive example. Okay. Now let's first take the specific, develop the specific boundary hypothesis. That is S1. For the example, after considering the example 1, this just S boundary work in more similar way that finders algorithm works. No. So for the given example, compare the value of every attributes like 1 to 1, 5 versus sunny, which is more, S boundary is specific. So it has to move towards the generalization. Okay, so we have to generalize. So the 5 is more specific, but sunny is more general than 5. No, so replace this 5 by sunny. Next, here is a specific value warm, comparatively 5. Warm is more general. So replace in such a way all the attribute values. Now, once the specific boundary is established, next we have to come for the general boundary. General boundary initially having more general value. Nothing more than question mark is general. So we have to move towards specific case, specific boundary all question mark is there after considering G1, since this one, Sunny is there, here the question mark in the hypothesis, since consider the likewise all other attributes. Example 2, after considering 1, the hypothesis set for S1 and G1 will be as given here. Now consider the example 2. The example 2 here takes the value sunny, warm, high, strong, warm, same. And also it is again a positive example. So now let's see how the S boundary is developed. Here the hypothesis for S boundary is S2, which is actually here sunny. The example 2 also sunny. Okay, keep it as sunny. And the second attribute warm. In example 2 also warm, keep it as warm. And here in S1, third attribute is normal, but in example 2, third attribute is high. So there is a mismatch. So replace it with question mark. Similarly, for all other 3 attributes, the same, there is no mismatch found, so keep it as it is. Right? So this is how S2 is the resultant hypothesis after considering example 2. Now come to G2. So this is more general than this one, right? So keep question marks are going to be kept. The turn to the third example. Third example have attribute values rainy, cold, high, strong, warm, and change. But it is a negative example because the enjoys 4 concept here is no, right? So since this is a negative example, as like our finders algorithm, S boundary, simply ignore that example. So there is not at all going to be changed. So whatever is the S2 is going to be copied here for S3. But in case of G boundary, that considers this negative example too. What it will do is, since G is, this is inconsistent, this all question mark for positive only. But for negative, it becomes inconsistent. So the general candidates by replacing every question mark with its opposite value. Because if since the rainy, cold, high, strong, warm change leads to negative, suppose if it has to be turned to positive, what must be here? That just a simple assumption is positive, opposite value. So with the opposite value, every question mark is going to be replaced. Likewise, the first hypothesis, what we generate as the first question mark is corresponding with the first attribute value, which is rainy. If you put the opposite value, that is sunny. So the hypothesis candidate 1 is generated as sunny, all 5 question marks. Next, the second question mark here, here in this example, cold is there. What is the opposite value? With that, you have to, the opposite value is considered only those examples which has been already studied. So amongst these 2 examples, warm is the opposite value, only find out. So replace that with warm, right? Cold, yeah. Okay. G3 now started generating candidates for example 3. The first candidate will be the one considering the first attribute, right? So here in G2, the first attribute is question mark. In example 3, it is rainy. Substitute with the alternative, that is opposite value. So the candidate generated is sunny with all other are question mark. Next, here the second attribute question mark, but example 3, it is cold. So opposite is warm. And the third attribute is question mark. Example, it is high. So opposite is normal. Then the fourth attribute is strong. If you see here, there is no opposite value. So leave it. And the fifth attribute, here up to the studied exercise examples, there is nothing opposite fine. So that also will be left. And the sixth attribute, here it seems to be change, but opposite here is same. So 4 candidates generated. So after this third example considered, there are 4 candidates generated. So now this is the time to eliminate those hypotheses, candidate hypotheses, which are all inconsistent. So first candidate is sunny, all question mark. This is consistent with all positive examples, EX1 and EX2. So accept it. Because EX1, EX2, the first value is sunny. So they are consistent. So here we have to look at only alone. Right? So the next second candidate also consistent with the positive examples, EX1 and EX2, so accept it. The third one is also consistent with the EX1, example 1, but not with the example 2. Because example 2, in place of normal, there is something called warm, right? So that it is not consistent with the example 2, so eliminate it. And candidate, next candidate C4 is consistent with both examples EX1 and EX2, so accept it. So only one candidate is eliminated after all three are accepted. So S3 already we have formulated. Now G3 will be the space consisting of three hypotheses, right? Now the fourth example is considered. This fourth example is a positive example. Now we have to generate the S4 since comparatively first attribute is same, keep it. Second attribute also same, keep it. Third attribute more general is question mark, so keep it. The fourth attribute, both are strong, keep it. The fifth attribute here is warm. And in example, there is cool. So mismatch, so keep replaced by question mark. Similarly for the sixth attribute. Here is same, but in example it says change. So there is a difference. So replace with the more general value question mark. Now the S space is over. G space, for all three hypotheses, we have to check whether this example hypotheses are consistent with the example 4. The first hypothesis is sunny, all question mark, right? Here is inconsistent because, and the second hypothesis also consistent with example 4. And but the third one, the last attribute value is same, but in the example it is changed. So there is a mismatch. So it is inconsistent. So eliminate the third hypothesis. So after considering fourth example, this candidate hypothesis, okay, it will be kept. The only two hypotheses are consistent with all examples. So G4 will be having only two hypotheses like this, right? Now next we have to move mapping the S boundary with the G boundary, right? We have to create the final version space. The G boundary is having two hypotheses, S boundary is having only one hypothesis. Now, this first hypothesis in the GS, and we have to generate candidates for it by simply replacing value only it is warm, right? And the next is only the replacing the fourth value, which is strong, right? Okay, this hypothesis is replaced like this. And this hypothesis, second hypothesis in G space, is replaced like this. Sunny, warm, the first candidate is changed. And there is another chance to change the fourth candidate. Yeah. Look at here. Wherever, because S boundary is having three specific values. Here only one specific value in every hypothesis. So replace, take the chance. Replace with the second value, replace with the fourth value. Similarly, second and fourth value. So now, amongst these candidate, the sunny, warm, all question mark is occurring two times. So it is going to be removed. One occurrence, repetition is removed, right? So after removing repetition, the hypothesis version space, three boundary hypotheses and intermittent hypothesis are of 3. So totally 6 consistent hypotheses is generated finally in the version space, right? So the overall explanation here so far, we is initialized all 5, G0 is initialized all question mark up to G2, this is not changing. But after considering example 1 and 2, S boundary is changed, right? This is what explanation given. After the third example, S boundary doesn't going to respond because it is a negative example, but G boundary will generate the candidate set. In the candidate set, what is generated will be eliminated according to the consistency. Those consistent candidate will be kept. Only three are consistent, we are keeping it. And then finally, the fourth example considered, since it is a positive example, S boundary also reacted to change its attribute value so that the fourth hypothesis is formed. And fourth level of hypothesis is formed in S boundary. In G boundary, the third candidate is not consistent, so it is removed. Only two candidate hypotheses are consistent. So G4 going to carry only these two hypotheses. And finally, this is what the generation person space generation in concurrence with the G4 in concurrence with the S4. So whatever is repeated, it will be eliminated. Finally, we have G boundary, we have two hypotheses. S boundary, we have one hypothesis. And intermittent, we have three hypotheses. Totally six hypotheses generated at the end of the final version space. Right? So now, elimination algorithm will converge towards the hypothesis that correctly describe the target concept, provided there are no errors in the training example and there is some hypothesis in the hypothesis space H that correctly describes the target concept, right? And then if suppose convergence stage, if the new instance comes, this is the new instance for which the concept is not learned, right? The new instant, and what may be the probable concept. Here, according to our hypothesis, this new instance will be predicted as a enjoy sport, yes. So this is a positive concept. And suppose if this new instance comes, for this concept will be learned from our final Western space that it is a negative instance. It will be classified, this question mark will be replaced by no. So this is since the new in space, Western space, will correctly classify them into respective classes, respective concepts. So that's why the algorithm converge. Thank you for listening. Let's meet on the next session. Thank you.